Okay, I'm going to go over an example of a three-dimensional model and how that might work. I'm going to do this in Excel, but obviously climate scientists would use supercomputers and write programs in different kinds of computer languages. But this should show you the principle behind it. So what I'm going to do is I'm going to assume that I can break up the planet into a grid or into a bunch of cells. In this case, I have 9 cells, 3 by 3. And these might correspond to something like latitude and longitude. So just to show that, I might have longitude going left to right, and latitude, say I'm in the southern hemisphere, for example, is going to be increasing from the equator down or something like that. Again, this is just an example, but just to try and tie it into what we're reading in chapter 14 of the textbook. So we could start with some physical quantity. So I'm calling this group of cells some physical quantity, and the quantity is arranged by geography. We'll just say, to begin with, every cell on the surface of the planet has an equal quantity. It might be something like cloud cover or precipitation, CO2, anything related to climate. And the next thing we want to do is then assume somehow those physical quantities can transfer from cell to cell. So if it were cloud cover, for example, it could move around the planet through wind and things like that. If it were CO2, it would mix with the ocean and with the atmosphere and things you read about in chapter 13. And so if we have ideas about how that happens, we can develop another group of cells that describes how those quantities are moving around. So before we get into those, let me just say I'm going to assume that this physical quantity is going to move in a way that it moves diagonally. So we're going to have movement of the quantity that does something like this. Let me just make that a little clearer to see. So we have something like this. If some amount of this quantity moves from this cell, it's going to move into this cell. And then if it moves out of this cell, it moves into this cell here. So from A1 to B2 to C3. And similarly, it might move from B1 to C2. And it could also, since we have this rule, it could move from A2 to B3. And what I'm going to assume is that since this, whatever this physical quantity is, I assume it's conserved, so it can't leave the cells. If it moves from C3 here out diagonally, I'm going to assume it just wraps back around to A1. And similarly, in the corners here for C1, it might move out of C1, but it's going to wrap back around into C1. So you'll see how that works in just a minute. So as this quantity moves out of a cell like A1, what I'm going to do is assume that, again, this is just to show you the principle, that the quantity, the amount of the quantity that moves out of a cell is related to its location. So what I'm going to do is I'm going to assume that the quantity that moves out is the product between the latitude and the longitude. So the amount that leaves A1 is going to be 1 times 1. So that'll be a -1. The quantity that leaves cell B2, that's 2 in longitude and 2 in latitude, so that'll be 2 times 2, so I'll lose 4 here. And I'm just going to keep going along the diagonal. For C3, that's a latitude and longitude of 3 and 3, so we'll lose 3 times 3 here, that's 9. When that 9 leaves here, it's going to wrap around and come back to A1, so even though A1 is losing 1 times 1, it's going to gain 9. Okay, so let me just show you how that would work set up in Excel. We're going to have what's called a loss matrix, which is the amount that's leaving the cell. So this -1 here is going to move to this middle one here. This -4 is going to leave that middle cell and move into this bottom right cell. and that -9 is going to wrap around back up to the top. Similarly, -2 here moves down to where the -6 is, but the -6 moves around by wrapping back up into here, and the -3 wraps back around onto itself. So this is the amount that each cell will lose over each time step of the simulation. And then we have a gain matrix because when these numbers wrap around or move from one to the other, each cell gains some amount. So this 1 that's being lost here moves into the middle, so this gains 1. This 4 that's leaving the middle cell here goes to here, so that bottom right cell gains 4. And this will happen over each time step of the simulation. So we're going to have some initial time equal to 0 matrix that's this physical quantity by geographic cell that's up here. We'll start with 100. After one time step, we have to take into account this loss and this gain. And then in the next time step, we take the new physical quantity by geographic cell and run the loss and gain matrix again in order to continue the simulation through time. And the time step or the time interval could be days or years or months, decades, whatever it might be, that's associated with the change in the physical quantity around the planet. Okay, so in Excel, let's see, here's time equal to 0, everything is 100, and here's the loss matrix here, and here's the gain matrix. If there were no losses or gains, then after some amount of time, then we would have the same amount of physical quantity, and if we look at a later time, it would be the same again. But instead, we have these losses. So instead of this being equal to its original value, what I have to do is take that original value and add the loss and add the gain. So I've lost 1 and gained 9, so that's a net gain of 8. And I can continue that calculation just by moving that over, copying it, and copying it down. Or you can type in the formula again, however you like. And notice this one is now equal to the first time interval because I've set it equal to what it was at the previous time step. So what I need to do is instead take the previous time step, add the loss, and add the gain again. And so I've gained another 8 because I lost 1 and added 9. So 108 plus 8 is 116, and I can copy that into the other cells and copy it down. And we can see how this grid of cells that would mean something related to the geography of the planet, we can look at how different physical quantities are moving around if we know something about the physics and climatology, and we can develop these pretty complex weather models by looking at how all these physical quantities are flowing around the planet.